So,
yes, the same one. Choose the same one.
yes.
Okay.
Play game.
Yes.
Environment, a foundation of this vision.
It's better. It's better than these already. So we stepped.
It's not going to the speakers, which is
Aye, aye, aye.
it's not going to the speakers. It can't go to the speakers because yeah, because the HDMI is not connected to the.
Okay.
It's fine. No, it's good. No, it's good. It's good. It's just too loud here. Can you make a gesture when you are going to play the video because I need to turn down the volume because it's
Oh,
super loud.
so should I turn down the volume in the
that
video?
would be great.
Hold on.
No. Actually, keep it loud for the room.
Yes.
But I will just.
So you will adjust? Okay. Okay, good.
It does because it doesn't go to the mixer.
Okay, so just.
It's fine. You can just lower the volume in post.
All right. Do you want to put this one back for now, or do you want to put this one back for now? Okay, great.
Sharad, would you like to do a sound check as well with your?
I don't have any sound.
That's fine. That's fine. We like that. Okay.
So here?
Yes.
Okay, good.
Okay. At some point, if you guys move out of the frame too much, we're going to do like a dance for you to show you where to go. So don't step too far that way, especially when you're presenting the slides. Because we have a small frame. We have a small frame while you're presenting the slides.
Okay.
When you're not presenting anymore and you're just talking, we'll have to adjust it.
Okay.
Because he's first. When you're not presenting anymore and you're just talking, we will then do a widescreen and then you can walk around a little bit, but not too much. We might sometimes, I will hold up probably a sign with like a microphone, and that means that you have to stand a little bit closer to the microphone. Or you have to talk into the microphone because we can't hear you. Right? So I will just write microphone on a piece of paper, and I'll hold it up.
Thank you.
So don't be afraid or anything. We will not
Yes.
interrupt your talk for the time. So if you go over the time, it's really not an issue.
How much time do we have?
45 minutes.
Okay.
Because for seniors, we do really, you have enough time. Just don't go on for 2 hours.
I know what it is. It's because it has a lot of videos and.
Good.
But yeah, normally just sometimes have a look at us. If we're like waving our arms, we're like telling you which direction to stand. So that's all. Okay. Seems like it's working. That's
Yeah.
good.
I just want to check something.
Is there anything particular? I'm spoiling myself. Spoiler.
Okay, welcome. Good afternoon. It's already now the 10th seminar that takes place today, so it's a milestone, the 10th. And before I give the word to Shirley to introduce the speakers of today and the show of today, it's time for advertisements. So the billboard, the virtual billboard, is already hanging because tomorrow is also the second forum, and it's on sustainable robotic technologies. So mostly we speak about applications, but also the robot itself has enabling and disabling roles towards sustainability, which will be the topic of tomorrow. So please join virtually or physically. But I think most of the people here in the room will come physically, but especially for the persons online, please, if you have time available, jump in. And then I give the word to Shirley to introduce the speakers.
Thank you, Bram. The first speaker is Professor Feron from King Abdullah University of Science and Technology in Saudi Arabia. He specialized in electrical, computer, and mechanical engineering. And before this, he also conducted research in France, in the United States. And his main research interests include fundamental concepts of control systems, optimization theory, and computer science to address problems in aerospace, transportation engineering, including air transportation, aerial robotics, software and system certification, and human-machine interaction. He's also increasingly interested in the marine environment. I would like you to welcome Professor Feron.
Thank you, dear Shirley, for the kind introduction. So what I'm going to do is first switch computers. There goes the advertisement. And we should be good very quickly. Okay. So the main topic of the talk today is this thing they call Ariadne. I explain you why later. But I will be also talking about other topics afterwards. So the core message of the talk is when it comes to robotics and autonomy, always have a plan B ahead and available at any time. Plan A is usually what people think a lot about. Plan B is what people should think about as soon as you end up working with embedded systems that could kill you. So before that, I just want to make a quick introduction of KAUST, and then I will talk about the various aspects of this Plan B engineering. And then I will give you some recent updates that may be better aligned with the thread of these workshops. So first, King Abdullah University of Science and Technology. So I thought it's a sufficiently strange university that it should be introduced. It's a university in Saudi Arabia. It was started by King Abdullah, who was the king prior to the current one, which is King Salman. And he said he wanted a university that is world class and that people will enjoy going to. And it has several and interesting characteristics from the viewpoint of a university which is otherwise located in Saudi Arabia. So there is a graduate education, only about 200 professors, about 1,600 students, also a large number of support people and engineers. It's a university modeled after the US system, including endowment-wise. It has $20 billion of endowment. And so that means the university is doing financially pretty well. It's the first mixed-gender university in the Kingdom of Saudi Arabia. So it's a university which is although it's in Saudi Arabia, the dress code is actually very relaxed on the one hand, and on the other hand, yes, you know, this incredible thing like boys and girls can be next to each other when they study. The focus is, I mean, it's very nerdy, right? You talk about physical, biological, computational, math, sciences, and engineering. So it's, they like to compare themselves to Caltech because of the size and the focuses. The only problem is there's not UCLA nearby or University of Southern California nearby. So we're really a technological university, sort of located, well, it's a gated campus, which is directly on the trajectory of missiles leaving Yemen and going to one of the neighbors up north. And so it's interesting. This is the Red Sea. So again, there is quite a bit of action in the Red Sea. But somehow we still manage to have a campus which otherwise looks like a sea resort with a university problem. We have these beautiful research buildings here. I mean, they could look small in the picture, but they're pretty massive. And we have a nice library. There is a mosque in the middle of the campus. There is an even more beautiful mosque here. And I mean, the sea resort part you start seeing here a little bit, but some of the people have their own pleasure boat there, so they can go on the Red Sea and have a little bit of fun. And I hope to show you a little bit of that later. So it's a US-style institution. You know, courses with teaching assistants, grading on A, B, C, D, and F scale, etc., 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 qualifying examinations for the PhD researchers' proposals, but again, the location is quite nice. Now is probably the end of the best season. You see, more or less when the nice season begins in Belgium is when the nice season ends in Saudi. The nice season runs from about end of October to mid-April because temperatures are nice. How should I say that? Grass grows, but then after that they turn the oven on, and then temperatures can go up to 50 centigrade in the summer, which together with an extremely high humidity level due to the proximity to the sea explains why many researchers then choose to go elsewhere for the summer. For example, I will be in the US this coming summer. So, when we're talking about not only robotic systems, but in general large systems that could kill you, safety becomes very important and start permeating all aspects of what you do with them. First, when you design a safety critical system, it is always better to follow like specific processes such as what's called the V diagram, a concept that came from Germany in the 1980s. And it says essentially think before you build. And I mean, there are like several ways you think about that. It's taught by, usually in France, it was taught to kids starting age 7. At age 7, you're supposed to reason. So think before you do. And then it's sort of repeated in many different emphases. But it never hurts to remind people to think before they do. It's amazing how many times we forget to think before we build things. And I'm the first victim of, or the first perpetrator of this sad habit. There are like very specific guidelines available in terms of, for example, software design and certification. There are guidelines about system architectures. there are regulations or advisory documents about various things related, for example, to what do we do. I mean, something as simple as now that we cannot buy a single core processors anymore. How do we insert multi-core processors in the next generation of Airbus A320s? When you think about it, it's important because if somebody told you that they had no clue about what processors they are currently using in order to fly the airplane, I doubt you would be boarding an A320 as comfortably as you do now, which is you don't think about it. Of course, there are technologies that come with that, requirements tracking, fault tree analysis, failure mode and effect analysis, static software analysis, and also what people call dynamic software analysis, which looks very much like simulation. Testing, safety by design, and I will be talking a little bit about this in the rest of my presentation. And of course, there are educational effort. I hope things are not too small, but I have a course named Cyber Physical System Design and Analysis, which I started talking at Georgia Tech, but since it's an online course, I decided that I would bring it with me at King Abdullah University of Science and Technology, because it costs me almost zero effort to put the course anywhere I want, given that all the lectures are online. It seems to be working, and as a result, I'm the only professor who teaches 3 courses per year at KAUST. Most people teach 2 courses, and some even teach 1 course per year. We're blessed in that regard. So where do I want to go from here? Well, we have a software revolution. We have powerful new algorithms for system autonomy. We have new sensory capabilities. We have, throw that random, we can now have image processing systems, tomography, LiDAR, radar, sonar systems for a lot less money, for a much lower price than we used to. And we have tons of new algorithms for behavior planning and execution. And these algorithms are a matter of concern, which is, yes, but what if your system malfunctions? There are like lots of algorithms we're very tempted to use, but they're not necessarily extremely reliable. And so what I wanted to give you is an example of what an unreliable algorithm can take to. So the worst system in terms of generating unreliable algorithms is the human. So there was a flight from Wichita State University to somewhere in Utah, where the pilots decided to take a nice scenic route in order for the teams for the sports team that was on the aircraft to see what flying inside the valley inside a valley would feel like. So they were basically below a mountain level, and people were enjoying the line sight, the views, except for one thing. The valley ended up with a wall. So when the pilots realized, oh my God, there's no exit point here, well, they essentially attempted to make a U-turn, but an aircraft takes a lot more room than you think in order to make a U-turn, and it ended up crashing. So the idea of Ariadne, and again, and I'll tell you why I call it that way, is all air transportation operations, but in fact all safety critical operations should be planned, designed, and performed under the constraint that at least one sequence of actions has been explicitly computed that will take the system out of trouble. And this must be the case for any known significantly likely mishap happening to the system. In other terms, you should have a plan B available, ready to go, for any problem that you know could happen. Okay. And why do I call it Ariadne? It's because of the mythological character, Ariadne, who was madly in love with a fellow named Theseus. And, but Theseus had been tasked and sent to Crete in order to kill a monster named the Minotaur. And Ariadne was the daughter of the king of Crete, Minos. And as I said, she was madly in love with him. So she feared less the ability for this Theseus to kill the Minotaur, and more for the quite high possibility that he never be able to escape the Labyrinth, which is the official name, I mean, that we use, of course, Labyrinth, in French at least, to indicate a maze. And it was designed by the very smart person named Deadalus, who then flew, unlike his son, Icarus, from Crete to Greece. And so Ariadne needed, and the reputation of this labyrinth is what you got in, you could never get out. And so what she did is say, yep, I'm going to take a spool of thread, I'm going to attach one end of the spool of thread to a ring at the entrance, and then I'm going to tell my beloved lover to keep the other end and to unroll the spool of thread as he makes progress inside the labyrinth to eventually find and kill the Minotaur. Okay, so that's why I call it Ariadne. I think it's one of the first known cases where you know, you can get into an adventure, you can do like very extraordinary things, but you keep knowing your way back out of trouble at any time. There are other cases of like similar matters. Up on my thumb, in French, Le Petit Pousset follows the same philosophy, whereby well, he loved his parents, but he was not totally trusting their love when they were taken in the woods. In fact, in order to abandon the kids in the middle of the woods. So Le Petit Pousset. How do you say that in Flemish? There must be a name for it. Klein? Okay, thank you. So he filled his pockets with little white stones, and you know, dropped the white stones behind him while they were making progress towards the inside the forest. And then when the parents effectively abandoned their kids, you just say, well, we're just going to be following the white stone trails and to get back to home, which they did, except the second time. Okay, so there was a problem because the second time he did, there was no white stones, so he put bread crumbles instead, but then the birds swallowed the bread crumbles. It's bad luck. So what are plan Bs for aviation? So for example, when you fly, the first thing I learned when taking my flying lessons is when you fly a small aircraft, especially a small aircraft with a single engine, everything, okay, never lose sight of a possible landing site at any time, okay, at any time. So in the US, they say, okay, highways are fine, but golf courses are less dangerous to land on. I mean, you can land on short surfaces. So that, in fact, you really should plan your flight keeping in mind where you're going to land, and especially golf courses, you know, like nice fields. All these things should be kept in mind, and flying over water for long distance is not necessarily advised. So is flying over dense forests for quite a while. There are changes to that, because some aircraft now are able to, I mean, some people are able to survive even though their aircraft doesn't land. For example, there is a new generation of aircraft made by Cirrus that have a parachute. So that's, of course, if you have this parachute, you can also sort of save yourself from trouble if you fly over a forest. This parachute is going to slow you down. But anyway, you know, talking about flying over the oceans, there you also have to be very careful. And much of the flight that you take, the transoceanic flight, are still, in terms of trajectory planning, constrained by availability of an alternate airport within flying reach. In this case, assuming that, for example, if you have two engines, then one might fail, but the other won't. Okay. For twin-engine aircraft, currently the maximum time you should be away from a backup airport at any time during the flight is 180 minutes. But it used to be 60 minutes, so the aircraft had to fly much further north in order to basically stay in touch and have alternate airports available to them all along the flight. Okay, the big change was when Airbus came up with the first twin-engine aircraft, the A300, that was actually allowed to lose an engine and still have to be no more than about 120 minutes flight. That's why, now we fly mostly aircraft with two engines, whereas in order to get the same kind of flight time and trajectories before, you had to fly in aircraft with 3 or 4 engines. Okay, so I thought it was kind of neat to say, well, okay, so Plan B is everywhere. As soon as you do things that are safety critical, Plan B is everywhere. And so I'm starting to think about it, applying it to other concepts. I've been talking, but here's a quick view of how a flight happens. You take off from New York, then as soon as you take off from New York, of course you always have the option of going back to New York, but past a certain distance, your backup airport is going to be Bangor Airport. Then once you go further from that airport, you basically keep having like a virtual tie to an airport nearby. Gander is very well known. It's interesting. It's a location that has 4,000 inhabitants and a runway that can accept an Airbus A380. So you can imagine like a gigantic runway with basically a minuscule terminal and only 4,000 people there. Guess what? It was very useful on 9/11, 2001, when everybody was told to land right away. So there were like a bunch of aircraft that landed in Gander, and pretty soon the whole village of Gander became like a giant hotel, bed and breakfast to be more precise, for like the thousands of passengers that landed there at any time. So you keep doing that, and then this is where this is your backup airport somewhere in Greenland, and then it keeps going. Creating these backup airports, having them always available until, of course, you arrive to destination. So in air traffic control, people do that also. They manage their traffic with always these sort of what-if questions in mind. So, for example, when you fly, if there is a risk of congestion at Brussels airport, for example, maybe a bad weather incident, air traffic controllers will always arrange such that, well, if you cannot fly to Brussels anymore, at least not immediately, then at least you will be able to, for a while, do racetrack patterns that will allow you to stay in place for a little while. And then when I talk to one of, and then of course what the idea is then, as you keep going and making progress towards your goal, you keep making sure that you have a racetrack pattern available ahead of you, not only for one aircraft, but of course for more. After all, many aircraft want to fly to Brussels, and the like for Heathrow and Paris de Gaulle and JFK, John Fitzgerald Kennedy Airport in America. The only thing is that when I talked about this to a professional pilot, they said they hate racetrack patterns because they start thinking, well, this is a backup solution for me at this point, but as sooner or later, I'm going to run out of fuel. So they want, if possible, that beyond your racetrack pattern, you have an alternate airport available so that you can, in the absolute worst case, land, because land is being landed is really the only time when you landed and stopped, and then you're safe. So anyway, we actually implemented this in practice. Yes, so much of the research in the US when I was there is funded by the military, so there was a little DARPA program. And DARPA stands for Defense Advanced Research Project Agency. And there was an autonomy project whereby we were going to fly. Well, unfortunately, they didn't give us the opportunity to play with the real autonomous aircraft that was sort of the poster child of the project, which was made by Boeing, but by an ugly duckling that was retrofitted with the same avionics. And what we said is, well, we'd love to plan trajectories for this aircraft using integer programming, mixed integer programming. Now, integer programming is really powerful. It can work many times. It could have been other algorithms, by the way. It could have been, I know, simulated annealing, real-time simulated annealing, or real-time other searches. But it has one problem. Sometimes it flunks. And so what we wanted was that if the algorithm flunks, well, we not send the people who are inside that aircraft in the middle of nowhere. And sure, it flunked. But before flunking, what we asked is the algorithm is, well, since you're so smart, why don't you not only plan a trajectory for me to go to the next task, but also give me one of these racetracks that I can follow in case you sort of go missing in action. And so each time the aircraft flunked, it was the algorithm flunked. The aircraft at least had this way of immediately going towards a holding pattern, and then stay there until a miracle happens of the mixed integer programming algorithm recovers or what. And one of the thank you notes we got from the pilot is that our guidance strategy at least did not throw them directly over Los Angeles. This is a flight test area which was close to Los Angeles. So at least we're not flying over Los Angeles now. We're staying within our area. And yes, we were flunking often, but we were flunking successfully. And then we started thinking about, the extent to which that linked to some of the research we had been doing earlier. And then here is one that Emmanuel may appreciate, which was, so how do you go safely from one point in your state space to another point in your state space? Well, what you do is you pave your state space with a series of operating points, and you pay, and together with the operating points, which could be think as virtual waypoints, you construct Lyapunov functions and really invariant level sets around each one of these equilibria in such a way that when you go and say go from here to there, you never lose the opportunity to sort of go to an intermediate equilibrium in case you have a problem with the next waypoint, if I may say. So you don't really schedule waypoints. Instead, you schedule Lyapunov functions, and each time you and you switch your Lyapunov function when you realize, oh, I can go further. Okay, I can go further. I'm inside the Lyapunov function of a further out operating point. Let me do that, and then you keep doing this, and then boom, 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 boom. You eventually, hopefully, arrive at your destination. And so I'm finally understanding some of what Professor Garon likes working on, and then I think, oh wait, there are like similarities. And then we are actually a person who implemented this in something real and worked really well is Emilio Frazzoli, with whom I and Munzer Dahle were working with in the early 2000s. And he said, you know, we can almost like plan these operating points ahead, I mean, in real time. So we fly, and as we fly, we sort of create these sort of operating points on the flight. And what we do is we do partial planning towards those operating points, and we hope by the time we may have to choose and go to that operating point, that equilibrium, okay, we'll have made enough progress that we can go to finally our final target. So if you're growing your path as you sort of make, so you're planning as you make progress, but you're planning with the constraint that the tip of every trajectory that is optional to you ends with a safe point. And that worked really well. I talked to him afterwards. He said yes, and this is the way we also did our software for his company named Autonomy, autonomous car company that he built at Singapore and sold in 2017. There are other interesting stories about this. Going back to air transportation, very often when you fly from Europe to New York, the truth is you don't fly to New York. You fly to Gander Airport. Why is that? Well, it's because you will take off and you will be allowed to fly only if you can guarantee with 99.9999999% chance that you will have all the fuel necessary to cross the Atlantic. And so you first plan your flight to Gander because it's close, okay? It's close enough that you can say, I can fly easily from here to there. And what they do is they fly from here to there, but of course at this point, they call air traffic control and say, we'd like to change our plan. We now have enough fuel in order to go to New York. And so the backup is in fact the nominal plan, and the nominal plan is sort of incident to the flight. So what is planned is what can be done with 99.999% chances, and where you want to go is where you have only 99 chance out of 100 to make it. And sure enough, there are like a few flights every year that thought they were going from Paris or Brussels to New York, but the people find themselves landing in the middle of nowhere instead in order to refuel. So anyway, it's an obsession in air traffic control. And so that was the subject I gave to an extraordinary pilot at KAUST. She was an American F-15 experimental test pilot. She had checked out all the most recent F-15 aircraft that the US generously sold to Saudi Arabia. And she was interested in formation flight. So formation flight is when you have several aircraft flying next to each other, the way geese fly in formation. And the aircraft behind can take advantage of the vortex shed behind the front aircraft in order to get a little bit of uplift and save a little bit of fuel. So I say, well, my poor, I told Safa, the student, I'm sorry because the formation flight has been like beaten to death as a problem. It's been looked at first by Boeing and in collaboration with UCLA. Then Airbus has the program Fellow Fly that's still going on. And the question is, yes, but did they think about the plan B? So what happens when an aircraft formation needs to deform? Because, for example, one of the aircraft craps out, or maybe an intruder comes in. And she looked at me and said, excellent question. And so she did her thesis pretty quickly on the subject. And we started developing like escape strategies. The fact that she was thoroughly used to formation flight in the military world, together with thoroughly used to aircraft, especially military aircraft, sort of not working well at some point in an unexpected fashion, certainly helped her expedite her thesis. She already had all the experimental knowledge available to her. Okay, so we had some fun doing this. There she is. Now she finished her thesis. She's back to Lebanon, trying to help the poorest of the poor survive. An interesting career. Experimental flight test pilot, turned basically doing charity work for the rest of her life. Except in Europe, I never thought I would meet somebody with such a wide range of activities. And so, ongoing directions. Well, one of them is coming soon. I love sailing. I have a sailboat, and I have a sailboat because I love to sail where nobody would want to rent me a boat. So we're going to cross a part of the Atlantic Ocean this coming summer. And guess what? You know, Plan B becomes like you become painfully aware of the necessity of Plan B. You see this little thing here? That's the life raft. Okay. It costs several $1,000s to buy one. It costs quite a bit of money to get it retrofitted. And oh boy, what's the temptation to say, well, I won't have the life raft inspected before I go because, well, it will work anyway. So, and then eventually we're still having it inspected so that we know that we will have a functional Plan B in case Plan A stinks. I mean, why am I saying you this is not to say that I'm proud of having a boat, but just to sort of tell you like how quickly it is possible to forego your Plan Bs, even though you get into safety critical solutions, okay? And another one is that you can see every day is defensive driving on the road. You know what defensive driving is? Defensive driving is always maintaining a good distance between you and the vehicle in front of you. You know, what, like maybe half of the population maybe pays attention to that, and the other are like stuck against your, and the others are like stuck behind you, sort of, flashing their light instead. So, but I must say that Belgium, for that regard, is very good in terms of at least very kind driving. I can cross any pedestrian crossing, and cars will be ready to stop in order to let me go through. I find it amazing. I find it amazing. I mean, in France, you'd be dead a long time ago. And so anyway, I want to give you now, for the last 5 minutes of my presentation, another subject that I'm working on, but I was not ready to show something when I talked with Anya about what to present. And, but it might be closer also to the spirit of this series of seminar and this year's session of the BrIAS. It's about robotics, much more robot-oriented, and the Red Sea. So, as I said, CAOS is a sea resort with a university problem. And so when thinking about the various activities I could undertake at CAOS, air transportation is one, but something related to the Red Sea is even better. When you think Red Sea, you think, I mean, you can think a lot of things, okay? My first answer was sharks, but others, they think, oh, Sharm el-Sheikh, the fancy resorts in Egypt and things like that. Turns out that there is fancier than Egypt for underwater tourism, and it is Saudi Arabia. So what are they doing? I'm going to play, what they're doing is they just realized that this was actually a fantastic wealth. Saudis are not very naval-oriented people. People who won the war a while ago for who's going to be the best and the leader happens to be more like people from the center of the country. But they recently discovered that their coastline is a treasure full of beautiful reefs, beautiful coral reefs that they should develop for two reasons. First of all, because they want to become more of a sort of multi-purpose tourism destination, as opposed to only one, which is Islam-oriented solution or destination. And second, they realized that the reefs in Saudi Arabia and all in the Red Sea are actually less vulnerable to global warming than the average population around the world. They still are subject to bleaching events, but those events are less catastrophic in the Red Sea because the reefs, the small animals that constitute the coral reef had to pass a test 7,000 years ago, a heat test before entering the Red Sea. Anyway, so...
No country is impervious to the ripples of global change. We must have a roadmap forward. Work is already being done to invest in our people, culture, economy, and environment. A foundation of this vision, NEOM, seeks to reimagine how we build for modern lives. To support these efforts, KAUST is taking the lead in supporting one of our most vital and vulnerable ecosystems. We are creating an integrated reef restoration model with the world's largest and most advanced coral nursery and a marine operation to protect and restore a 100-hectare reef adorning Shusha Island in the northern Red Sea, before beginning to support restoration across the region. So we invite you to follow our efforts to explore our reefscape through immersive virtual innovation as we embark on this first chapter in an unfolding legacy to celebrate the natural wonders of every corner of our shared world.
Isn't it interesting to hear that from the #1 exporter of oil in the world? So, well, they're also interested in their own future, and they realize, oh my God, this is a treasure. Okay, we've got to be careful about it. So well, let's face it, if they stopped exporting oil tomorrow, pretty much at least or a good half of this classroom would probably be hurting a lot. But so they look at this, and they're putting their wallet where their intents are. They're thinking about doing sort of becoming the powerhouse for reef development and maintenance, the world hub for that. I apologize. Let me take a little bit of more water. So there is something which is to be thought about, which is there are only 35 million Saudis. Not all of them are interested in the water. And they have 1,600 kilometers of coral reef coastline to take care of. So you can imagine that robotics comes very quickly into the picture because none of what they're talking about can be done only using human work power. It's just impossible. Maybe for the Shusha Island that you saw, you can still have it done by humans. But if you want to scale up to the entire coastline of Saudi, you have to rely on form of robots. So the first project I got interested in was roboticized survey. Roboticized survey of the environment, and what I've been thinking about and still building now are like towed robots, so underwater vehicles that are towed by surface vehicles, with the idea the underwater vehicle will be retrofitted only with the sensors, cameras, maybe sonars, a little bit of actuation, but that most of the power needed for this thing to move fast. Remember, 1,600 kilometers of coastline is not small. All the power would come from the surface boat. And with a corollary, which is these little underwater towed items would be allowed to operate close to the reef, whereas the towing boat on top of it would be staying away. You can tow something while, you can tow something which is not right behind you, but besides you. Anybody fishing in this room? So that, I love fishing. I have a sailboat, so I actually have little towed kites like this, and the kites, you can arrange them so that are like one side, the one goes on one side and the other goes on the other side. So that allows you to put 2 or 3 lines in parallel, so that you can increase your probability of catching fish, of course. So these are underwater little things, are kind of amazing little machines. We're currently building prototypes, and we're playing with them. We haven't gone at sea yet. Well, more precisely, we have gone at sea, but we started with a swimming pool test, and then we went to sea tests to see how this thing would work. And when they did the test, the poor thing was damaged because the sea state was too high. It was shaking so much that they were throwing up while trying to take pictures of this. And this is the view from. Hello. Hey, move on. Next. Okay. Good. These are the kind of views that you can get. For now, we're using only visual sensors, but we're talking about mounting acoustic sensors as well, in order to, make this machine increasingly useful, on the one hand, in terms of collecting data, but on the other hand, increasingly intelligent in terms of avoiding obstacles, for example. These things are often lost because they hit obstacles. And that also I know as a fisherman, because every year I have to buy a new load of these underwater kites for my fishing lines. It's not as expensive as what we're building in the lab, but anyway. So that ends my presentation, and I thank you very much for your attention.
So thank you very much for your interesting presentation. And I will start with a question online, and then I will move to the audience. So I start with a comment from Fabrizio Dabene and a following question. So Eric, very nice and interesting talk. I like the different approach towards AI certification based on Plan B. So the question instead is, from a control engineering point of view, what are, in your opinion, the main tools from our community that may turn useful for Ariadne? I saw LiAPNOB and optimization as main drivers. What about robust control and robustness?
So I would say that, I don't know if you have explicit techniques that we want to bring, but certainly explicit, sort of very clear philosophies. And one of them is always know that you're going to land somewhere safe. Don't take chances. And take chances at where you're going to go, but maintain the certainty that you're going to be fine. So in the controls community, it's sometimes named runtime assurance, meaning that you don't build your guarantees all ahead of time, but what you do is you build your guarantees on the fly. And so it's named runtime assurance. Plan B engineering. One example is, again, the regulator, how do you call it? Reference governor, developed by Emanuele and his gang. And so if I may say, there's this, I mean, what the control community does that nobody, that few other people think about, which is always safety, 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 safety. I think it's because the controls people started developing their thing on aircraft, and that safety was sort of the number one concern. You know, doesn't fly good, but it flies safe at least. And and it almost, I think it almost kills us in the following sense that in the meantime, while control people are obsessed with safety and stability of all sorts, then you have like lots of people who couldn't care less about that, and then they start showing like videos of machines doing amazing things. You say, but you don't have any proof of safety. You say, yeah, we don't care, it's nice. So I think controls can bring this sort of philosophy of no matter what, okay, make sure you're safe. No matter what you're doing, make sure you're safe at any time.
Okay, thank you. So I don't think that there are other questions online for the moment. So if there are questions from the audience.
Hi, thanks for your talk. It was very interesting. I learned a lot of new things, I think, about planes and flight roads. I'm very interested
You won't come to Saudi Arabia.
I also think a little bit more before boarding a plane
We have a nice
in the future.
oh, yes, okay, makes sense.
Yeah, and definitely I like scuba diving, so maybe Saudi Arabia will be one of the next destinations. And that was something I'm very interested in. I like the application of reef restoration. And I've seen organizations, they are replanting the corals outside, and then they're taking them and regrowing them, and also with robots. I was just wondering, how is your robot going to work? Because I didn't see that it's actually planting new corals.
So this one is just for survey.
Fertilizing? Oh,
this one is just for survey.
Okay.
And we thought about it. We're not the only ones, by the way, to have thought about it. There's a great company named Vertigo 3 Flying Fish in Australia, who said, well, for survey, you know, we can just tow something and then and let's see how much maneuverability we have. And they're actually now doing some survey in Saudi Arabia. And but yes, no, because planting, for example, from the nursery back to the ocean is not an easy exercise as well. We started looking at how they're doing it. I mean, there are many approaches, and the problem is always the same, which is, well, okay, so we could regrow maybe say 40 meter by 40 meter area, but then now we need to scale up to the whole Great Barrier. And it's like, gosh, I mean, how do we do that? So that's where really robotics is important, but not necessarily completely mature yet.
So it's more about collecting the baseline and knowing what the health state
for now,
of
yes,
the,
for what
of
we're
the
doing,
corals
yes.
is. Yeah,
but then
okay,
we're thinking about
so that would be the next step.
Over replanting.
Yeah.
And so, are you involved in any activities
nope,
related to that? Okay.
Me not. I don't know if anyone else.
Okay.
Thank you so much for your presentation. When we consider the Plan B approach in any construct, whether it's with AI or if it's with sailing, I think in order to have a Plan B, you have to have well-defined objective outcomes that you identify as disastrous, right?
Yes.
So
sinking is one.
Sinking is one. So the question I have related to AI, robotics, and exoskeletons is, will we be able to adapt to the catastrophic outcomes that we can't conceive of right now?
Yeah, but okay, so here's how the aviation has done it, okay? It's learned through history. At the beginning, they didn't care about anything, then boom, first accident happens. They say, this thing cannot happen anymore. So, for example, using engines with only single spark plugs, one spark plug per cylinder. Next thing you know, all the aeronautical engines have, as far as piston engines are concerned, have 2 spark plugs per cylinder. So that if one fails, the engine still works. It has 2 fuel pumps. It has 2 electric, so it has many copies of the same. That's one way to eliminate or to reduce considerably the risk. As far as the evolution of AI is concerned, I think people are they're learning, and I don't know if there is such a rigorous accounting for how to make sure that each time a new accident happens, it will never happen again. So I know in aviation they have to do it. They have to do it. So they are very the people who develop autonomous aircraft, I'm talking about aircraft that could hardly fit in this room, by the way. Okay, I'm not talking about small drones. I mean, they use AI because it's great to recognize lots of things on the ground and everything. But they always think, okay, well, so what's going to be my backup plan so that the FAA, the Federal Aviation Administration, eventually allows us to operate this vehicle, autonomously from its parking space all the way to the destination airport. So, and by the way, that's one of the nice things about aviation. It's still used by many people as the gold standard for what it is to make things safe. Okay, the gold standard is suffering these days. When if you read about Boeing, Boeing is suffering a little bit these days, but it's still considered the gold standard. And so, for example, Martial Hébert, who I think still is the director of the Robotics Institute, he said, well, we will be happy with AI in what we do, autonomous cars, healthcare, and things like that, but only when we are able to develop an environment as far as development and operation, which is as safe as aviation. And then he went on and said, do you worry about when you board an aircraft? Well, maybe a little more these days than usual because of these 737s that keep losing their doors. But in general, nevertheless, we're still quite confident when we board an aircraft. He said, you should be as confident when you board an autonomous car than as when you board an aircraft. And then, so there is some of that mentality that is percolating. And again, I mean, you know, is it possible to operate a ground vehicle safely and autonomously? I don't know, because I don't think it's possible to operate a ground vehicle safely today. I think that you know, each time I bike, I put my life in danger, and each time you drive and you're like, say on the highway, you actually put your life in danger, but less so than if you take a bike on the highway. By the way, aviation, it doesn't mean you should board your friend's aircraft. If anybody who owns an aircraft, it's safer to drive than to go fly with a friend.
Okay, we have time for one last question. If no, let's thank again Eric for the presentation. And I give the word to Shirley.
Yeah. Thank you for welcoming me here, and thank you to all the organizers. You know, it's my first extended stay in Brussels, and it's fantastic. It's fantastic. I'm going to ask for more.
So we'll have a short 10-minute break. So let's be back at 3:10, and then we'll hear our next presenter, which is Sharat. Hello, everyone. We're back here with our second speaker, Sharat Chandra Akala Devi. He is a scientist at Profactor in Austria. And Profactor is a non-university research institute focusing on applied research. He focuses on robotics and human-robot collaboration. And he's very interested in the seamless integration of robots into human environments. And also his work on activity recognition and novel robot interfaces highlights his innovative approach to programming robots. Sharat, it's now up to you. Thank you.
Thank you, Shirley, for the kind words. Robots can aid positively sustainability. They have shown quite some interesting applications towards changing, improving the climate, crisis. They are towards remanufacturing. They can improve the remanufacturing processes, and they have shown positive impact. And we have seen use cases where robots play a vital role. However, the aspects of sustainability and how the sustainability principles can be defined within robotics. How robots themselves are sustainable, it's quite a challenging question. So how do you define sustainability in robotic applications? And on the other side, how can robots themselves be sustainable? How can you manufacture robots themselves sustainably is quite a challenging question. Good afternoon, everyone. I'm Sharat Chandra Akala Devi from Profactor, and I'm here to present our work on intuitive interfaces and how to easily deploy robotic systems and how this aids in sustainability. Good. Going forward, the agenda for my talk today would be to give you the role of intuitive interfaces, what are different forms of human-robot interaction. Some examples. I will show you some intuitive interfaces, how to deploy robots, how to program robots. And I will also talk about physical collaboration of robotics. Yeah. And then I will show you some examples of robotic applications for sustainability, especially towards battery remanufacturing. And then I'll give you an outlook. Good. So now that I have your attention, I would like to also interact with you. So it is not just intuitive interfaces that I want to talk about, but I want to interact with the audience. So please fire up your mobile phones or smartphones or computers and scan the QR code, or you can just visit menti.com and then just enter this 8-digit code so that you are guided to a question. So just give me a second. I hope this works. It'll be back in a second. So. Great. So which sustainable development goals do you think collaborative robots can have most impact on? Do you think it is affordable and clean energy? Do you think it's industry, innovation, and infrastructure? Is it sustainable cities and communities? Is it responsible consumption and production? Or do you think it's none of them? Great, so industry, innovation, and infrastructure is winning, and responsible consumption and production as well, so. Good. So then going on to the next question, should I give it a second or two? Does it show? Yes. So which aspects of sustainability do you think collaborative robot excels in the most? So why should we use collaborative robots for sustainability? Is it reducing the waste, or to increase energy efficiency, to optimize processes, to do environmental monitoring, or are there other aspects that we have overlooked? I would be rather interested in the other aspects if there is somebody who can just shout it out. Great. It's nice to see quite some interaction from the audience, so thank you. Thank you for this. Very, very nice. Good. So now that I have your attention, then I will switch to my presentation now. Just give me a second. So, where am I from? I'm from Profactor. Profactor, as mentioned earlier, is a non-university research institute. We are established in 1995. We have about 105 employees. So this includes researchers, scientists, and also engineers. We are located in Austria. So our headquarters is in Steyr. We also have an office in Vienna. So for those of you who don't know where Steyr is, if you know Salzburg and Vienna, as I always say to people, just come to the center. That's where Steyr is, yeah? So if you're around in the area, just give me a call so that I can invite you to our labs and then show you our cool robots. We have a business plan of both bilateral projects with industries. So we do one-to-one projects with industries, and we also have quite a few funded projects. And overall, it's a 50-50 split right down at the center. And we are jointly owned by the Austrian Institute of Technology and the Upper Austrian Research. Our profile, we have two research areas. We have industrial assistance systems and additive micro and nano production. And we have different solutions. But for today, I will concentrate mainly on the industrial assistance systems and the flexible robotics and the perception and projection part of it. Coming to our portfolio, we have a lot of know-how on robotic processes, surface inspection, spatial augmented reality, post recognition, event recognition, and also the basic robotic processes like polishing, screwing operation, pick and place, and things like that. And we built upon these know-hows two main aspects: human-robot interaction, so how to interact, how users can easily interact with robots, and cognitive robotics, where we implement AI-based algorithms to improve the robotic processes. And we have quite a few success stories, collaborating with companies like Airbus, Daimler, BMW, and so on. So where we install our robotics solutions at their location when they come with a problem, and then solve the issues that they have. So coming back again to the talk. As I said, robotics have quite a substantial role to play in the coming years. They're already very much helping sustainable applications. However, the definition of sustainability and the sustainability, how to justify or how to define sustainability in a robotic application, the data, the tools, and the methodologies for defining this is quite lacking. And this also requires a lot of cross-collaboration between different fields of sciences. For the talk today, I will talk about different forms of human-robot interaction and how intuitive interfaces and physical collaboration play a role in this, and then how can we combine this towards sustainability. I will focus my talk towards Europe. So what's the the current situation in Europe, and also focus my talk towards human-robot interaction for manufacturing systems. So I don't focus my talk on all kinds of human-robot interaction, but I want to focus it on manufacturing systems. So we have now in Europe a situation where by 2060 it is estimated that out of 4 people, 3 people will be in a retirement phase. So there will be 1 person working for the whole 4 people. That's how they call it. So, and the cost of care is rising sharply. And if you are going towards your old age, taking care of you in the hospitals, that's become very, very costly. And on the other side, there is also a lot of skill drain in the industries. So you have people with quite high qualified workers who have so much knowledge, but as soon as they retire, this knowledge of their skills, it's completely drained. And then the new workers that are coming in, which is on one hand, it is difficult to find workers, and on the other hand, it is also very difficult to train them and to bring them to a skill level that is sufficient to have a good productivity and quality of the work. And the solution for this is to have a cooperation between humans and robots. So the idea is that humans are more flexible, they have good cognitive thinking capabilities in general, and they can deal with different kind of situations. And on the other hand, we have robotic systems which can do repetitive tasks, they can do heavy lifting, they are not tired at all. So combining the cognitive flexibility of humans with the physical capability of robotics is the way to go. So the idea is not to completely remove the workforce and automatize with complete robotic solutions. That is not possible, but to combine robots and humans so that they can join forces and then create new applications. So looking at a vision, this could be something of a vision in an industrial situation. A human is working with a robot. The human is teaching the robot a task. The robot is able to learn it, and then it can apply to different settings. And once the robot learns this, it can communicate with other robotic systems in the area. So this is how. I mean, it's a vision. It's not reality. We are working towards it. But this is a good vision to have. So when you talk about interacting with robots, there are different forms of interaction. So a simple on and off switch, which turns on the robot and off the switches of the robot, is some kind of interaction. So it's a very basic form of interaction. However, I would like to define 3 phases of interaction. I would like to call it as human-robot coexistence, where the human and the robot are in close proximity, but both entities are minding their own business. So there is no specific interaction per se. And then there is human-robot cooperation, where human and the robot are working on the same workpiece, but they have their own task related to that workpiece. And then finally, we have human-robot collaboration, where they are working on the same task. So they're doing the same task together as a joint unit. So that is what is collaboration. But when you look at it, the process speed towards safety requirements are going. The safety requirements are increasing from left to right, and the process speed is also going down. So this is one aspect we have to keep in mind towards the application and towards the field where we are applying it. So in some cases, coexistence might make sense. In some instances, cooperation. Collaboration does not always make sense. It is useful, definitely, but one has to really think about the scenario and what is feasible. And to interact with robots, there are 3 main requirements. So the interfaces that you have that you can interact with the robot, it should not be like a black box, or it should not be like a very complicated system. It should be an easy to use interface, like simply like your smartphone. How difficult is it to learn how using a smartphone is? Maybe you spend 5 minutes, 10 minutes. It should be that easy. You should have a safe interaction. The robot, when you interact with the robot, that's very, very critical that the robot should not harm the user. And then it should be flexible. So we don't want a robotic system working on only one task. We want it to have multiple tasks so that it is flexible, that you have return of investment for your robots. So that's how I see it. And I will only concentrate on 2 aspects for the talk, the easy to use interfaces and the flexibility. Traditional approaches, what we have to program robots, are very tedious. So they're often done using teach pendants or some very hard programming interfaces. They require a lot of effort to change. They're usually not very flexible, and they're very complicated to teach in. So if you want to program a robot to go to 2 points or 3 points, it takes hours to precisely teach the robot using these teach pendants. So what is the solution? So we said that we don't want to use the same robotic system for only one task. We want the robotic system to have multiple possibilities. Traditionally, we had industrial robots which stayed behind closed fences, and then they did the work again and again. So the same task was done repeatedly. But with the advent of collaborative robots, these traditional robots that once were behind closed fences are breaking the barriers and moving towards joining hand in hand with humans to collaboratively work with them. So that would be the solution, where collaborative robots are very easy to program. They should be easy to program, they should be flexible, and they should be safe. So one such solution is a programming interface we have at our company. It's a programming interface that can easily combine different sensors, different actuators. We call it an X-ROP system. So you have a task of screwing on the motor block. You have different sensors. You have a 2D camera, you have a depth sensor, you have IR lighting. How should be an interface programmed? So it should be as simple as a tablet. So you have to just teach in with a few clicks. So the task, how the robot is taught here is, it takes a reference scan of the motor block. The user then just kinesthetically moves the robot. he teaches the robot where to screw, yeah? What is the screwing location? And then just this is then encoded. So it just takes about half a minute or 1 minute maximum. And then the same, is done for the next position. And then that should be it. So you should just use what kind of interfaces feel natural to you. So you use a GUI-based interface. You used, you can directly touch the robot to move it around. And then you program the robot. And now the robot is ready to do the screwing operation. But that's nothing so fancy, yeah? The fancy thing is when there are some kind of deviations in the environment, yeah? So you don't have the same environment, the environment changes. So right now there is a workplace displacement, but the algorithms behind it are capable of adjusting to this change because you scan first how the motor block is, and then all the parameters are then adapted to this change in the position, and then the robot executes the program. And another example is, a bin picking application. This is something we developed in a lab just as a tool. So there is a robot. There are some objects it has to pick up, and then the user is given a tablet, and then the user just scans the objects and selects which objects should the robot pick up, and the robot then plans how to pick up those objects. So it should be that easy in a sense that you can just show, we can play. So these kind of interfaces do not require any sort of experience, any sort of special education, that you don't have to be a robot programmer. You can just use any non-expert user, non-programming expert can just use it. So you can just see the overlay in the background. You can simply select them, and then the robot then knows how to grasp them. So this is just an example. So all these examples right now are just maybe towards coexistence, yeah? The human and robot are more or less separated. I would like to show you an example of cooperation. So here we have a motor block again, the same screwing application. The robot is taught in where to screw. And the user is cooperating by screwing other places, yeah? So there is a process flow in the background. You can know what kind of progress you are making in the task. The robot is just minding its own business, yeah? But what happens when the user is coming in the way of the robot, yeah? So since we have cooperation, it could happen that the user is coming in the way of the robot. So it should still detect at least these aspects and then stop, and then tell you that that's an error, and then proceed with the task. So that's just an example for human-robot cooperation. So till now we have seen interfaces like GUIs and kinesthetic teaching where you're holding the robot. So let's go towards vision-based interaction. So where we use interfaces that do not obstruct, or you do not have to touch them. They're just sensors, cameras looking to the scene, and how this can be used as an interface. So we have a 360-degree camera. It's called a fisheye camera that has an overview of the complete floor. Then we shift the 360-degree input image to a rectilinear view so that we can observe what's going on in the scene, and then apply our algorithms on top of this. So this is what we do. So we have control over the complete factory floor, for example. And then we can estimate the 3D position of the users or the humans, yeah, and also the robotic systems, because they are articulated, yeah. So you can have a clear understanding what is a human, where is a human, how many humans are in the picture, what is the current position of them, which direction are they looking, how are they going around. And you can also do the same with the robotic system, yeah. So you can just, there is no need to connect to some interfaces. You can just switch on the camera, run the algorithm, and then just find out where the users are. How can this be used in an interaction scenario? How is this feasible? So you can initiate some kind of user stories where you want to initiate some kind of robotic action, and the robot is observing the factory floor, looking where everybody is, and then now a human is approaching the robot slowly, and then the system detects the human, and then you take a device to switch on the robot. It's a leap device which can detect gestures. And you have to note here that when the user is not looking at the robot, the interaction is not initiated. So now I will show you an example. when the user is looking at the robot and doing a gesture, it stops. But when he's looking away, yeah, it does not. Because this is the context that you include into the system. So it is not just taking only blind gestures, it is also taking the context, it is also taking where the human is looking, and you're combining this information to interact with the robot. And then there could be other use cases where you have robotic systems working at high speed, and you want to slow them down when the user is, or a human is coming close to them. So these kind of systems can be very, very useful. So you can observe, you can have a bird eye view of all different entities, different human workers working around, and then you can measure the distance, how far the human is, how close the human is, in which direction is the human looking, is a human intended to cooperate with the robot or not. And now, when you have situation where the robot is moving too fast and then the humans are coming closer, then it slows down. So this is how you can include these kind of interfaces, like which are visual. So they are not interfaces which are reliant on human touch or GUIs, especially. So these are interfaces based on vision systems. And there are other kind of interfaces we are working on. So till now we have seen robotic systems that you can touch. Yeah. So there are collaborative robotic systems that say that they are safe. Okay. So when they are moving in the vicinity, and if there is a human in the path, they will definitely hit the human. But the force values are calculated, and then they stop. But that's all that they can do. They can stop. There is no other interaction possible. But we have to think that there is this aspect of accidental collision that we want to definitely avoid. But there is also this aspect of deliberate interaction. Yeah. What if I just want to touch the robot to move it around? Yeah. What if the robot stops? So what we have done is we have used inkjet printing technology to print capacitive sensors. So these are very flexible. They can be bent. Yeah. And then you can wrap them around the robot. And using these kind of sensors, you can control the robot as well. So even if you touch the robot itself, depending on your gesture, it can work in different modes. Yeah. Now you're gesturing that you want to move the robot in a compliant mode. You can move it in any direction you want. You want to teach it a position, so you can just touch the sensor. It's a capacitive sensor, like on your phone, or yeah. And you can also use these kind of capacitive sensors to do kind of fine position teaching. Yeah. So if you are familiar with collaborative robots, you have these teach pendants that you have to touch and then really see near the robot where the robot is going. But here you can also use these printed sensors to just move the robot in X and Y and Z, and this is another use case. So that's also a very interesting interface. Good. So I've shown you how to program a task on the robot. Especially I told you how to do the screwing task. Yeah, you can just show way to do the screwing operation, how to encode it in GUI. But what about the low-level features? So screwing is not just showing it what is the position. Yeah, you have to show it how much force you have to apply, how much torque it's going to be. So for that we have interfaces called handheld interfaces. Because the human himself or herself is very well versed with the process. So what we do is we have regular screwing guns, which are equipped with tracking technologies, and then we want to record the data that is coming from these handheld interfaces, so that this can be then transferred to the robot, and the robot can then replicate these screwing technology or the screwing parameters. So you set up the system, and you calibrate it with respect to some kind of a reference. And then you want to, usually do a screwing operation. So the user is just simply picking up a screwing gun, as in the workplace, and then the user is just doing their own task. So you can just also give it this kind of handheld interface to a worker, and then the worker is just doing the task. Yeah. But what is happening in the background is the process parameters are then recorded. So what is the angle of approach? How high should the robot be? How what angle should the screw gun come down, and how much force and how much torque value should be applied? And then there is a digital world where this is recorded, and then you simply show in 1 or 2 examples or 3 examples maybe how this should be done. And then that's it. So these are handheld interfaces, which can also be used to record low-level process parameters. So all we are talking about right now is how to avoid programming, yeah? How to avoid, sitting in front of your computer, writing hundreds and hundreds of lines of code. This is not possible for normal workers, yeah? You cannot expect a factory worker to do programming. So we as researchers and developers should find out methodologies in which a normal worker at the factory floor can use these interfaces very quickly and then program tasks in the factory floor. And there is another example of physical assistance. Yeah. So it is not just programming robots around, but they should also actively help and assist workers. So we have also other interfaces that can track the user position, understand the intention, and then help the users to simply lift weights. So here the human is just guiding the robot, and then heavy weights can be easily lifted. So that's just an example of a physical assistive system. And to dive deeper into the physical assistive system, we have collaborative draping of carbon fiber parts. So there is a very nice EU project called DrapeBot, where we look into collaborative draping of carbon fibers. So it's a very huge robot. It has a payload of 150 kilos. And the part itself is very, you have to be very careful when you are moving with the part. It can easily bend, it can easily break. So there is a lot of ambience detection, so you detect where the human is, in which direction is a human walking, and the robot has to follow and then drape these kind of parts over the mold. So that's also an extended part of these physical assistive systems. So till now we have talked only about how humans can interact with robots, yeah? So how to program them, how to use them. But what about just the normal factory workers who are just going about their daily work, but they need assistance in their work? So how can you guide the workers during the process? So that is where we have the cognitive and the physical assistive units, yeah? This is an EU project called Inline, where we developed these two systems, yeah? So here we have different system components. Of course, we have the robot, but we have additional sensing unit. So this is just the same X-Rob technology that I showed you before, a robot with a screwing gun. Yeah. And the user comes in, places a part, and then we also have projected interfaces. So the system itself is guiding the worker what is the current process that the user has to do. So where to do a screwing operation, and which tool to pick up, and giving feedback on the task itself. Yeah. So when the user picks it up, the event is detected, and then you find out in which direction it should be moved, to which location it should be shifted. And once this is done, the state changes, and then the robot takes over. And then we again go on with the physical assistive system. So these kind of interfaces are not only helping you to interact with the robotic system to set up it for a task, but they're also very interesting for the users themselves. So if you have a very no voice user, so there is a worker joining the company today, how can they be trained? Yeah. So you don't want to spend expert time, like hours and hours teaching them. You can have such interfaces to guide them through the process by giving them hints, and then just go on about the work. So that's just as an example. Good. I will not go to the Blackboard project because of time, but I want to show this another project where it deploys the complete solution. So it is called Robox Task, where it just completely bypasses the coding aspect. So the task here is to simply use drag and drop operations. So we have such kind of an interface based on Blockly. So you can just drag and drop, and then you can just program the robots. What we assume here is that the robot knows how to pick up an object, and the robot knows how to place an object. Let's call it like this. But these skills are known, and then based on these skills, you can configure them by just dragging and dropping. Okay, the robot should do pick operation twice, place operation twice, and then it has to navigate from one location to the other location. So based on that, you have, I mean, it's a researcher here or a programmer here, but it's simply dragging and dropping the whole text. And using this interface, you can quickly build up complex operations. It's not that hard to really program complex operations. And what is happening in the background is it can generate the code that is required. So it is in the background generating the Python code that is required to control the robot and also to execute these tasks on the robot. So that's how, yeah, that's the code that is generated, for example. And then you can execute this. So before executing this, you want to first check it if it is working properly or not, yeah? So you have to have some kind of interface or some kind of a digital twin, let's call it like this, that you want to check your program and then go to the deployment. So we also have a digital twin where you can easily check the performance of the robot, and you can also validate the solution to see if how the control is going around. And finally, you can also go towards the deployment in the real world scenario. So I think it just comes up in a second. So yeah, so using such kind of a interface, so what we have seen till now is different interfaces like GUIs, different interfaces like kinesthetic teaching, different interfaces like visual-based sensors. All of them were more or less having to do with some kind of coexistence or training the robot or cooperating with them or coexisting with them. But I also told you that I would like to talk about human-robot collaboration as well, yeah? Collaborating physically with the robot, and how does collaboration go about? So to enable such efficient human-robot collaboration, we need to perceive and comprehend the environment. It is very, very critical that you understand how the environment is, what kind of objects do you have, what kind of, where the human is, what is the robot doing. You have to represent this as knowledge, and then you have to also reason about this task. So what is your current state, what is the human doing, and what can the robot do to help the user. And then you have to do this decision-making and replanning, and then interact with the human. So for that, we have a use case where we developed an action recognition system, a 3D object tracking system that is tracking objects. The action recognition system is tracking the human and finding out what actions the human is doing. And then we have a safe and trustworthy interaction, because we also see the visualization of the robot. And there is a feedback, and then this is how it looks like. So in the system, we have a robot with a gripper. It's a UR10 robot with a shrink gripper, which is electrical. We have 2 camera sensors, Connect 2 for action recognition, and then ASUS for object tracking. And we have on the right side, or just below there, some day-to-day objects. So the goal here was to collaboratively assemble a domestic appliance. So it's a steam cooker. And the goal here was to assemble this steam cooker in collaboration with the user. Find out what the user is doing, and then for the robot to predict what is the next part that is required, and then hand over this next part in a position suitable to the user. Yeah, the user might have different heights. The users might have different preferences. There are different categories in which the interaction could be. And we have an interface to showcase, some kind of visualization which predicts in which direction the robot is going to move. Yeah, to inform the user, okay, this is the direction the robot is going to move, and this is just to warn the user in case, yeah, if something unexpected happens. So now the user picks up a part, the action recognition system and the object tracking detects it. You characterize it as an event, and the robot is then initiated to pick up the required object. Let's call it like this, yeah. And then it is going to place it in a position that is suitable to the user. So it is going to track where the user is, what is the height of the user, and then position itself so that it becomes convenient for the user to mount such kind of objects. I mean, then it just goes on, but I will not spend too much time. It's just you can also find this video in the YouTube. But how does the robot know what is a task? Yeah, how does it know when to do what kind of interaction? How to really pace itself, okay, this is the current situation of the user, and this is how I have to interact with him so that the collaboration will happen. How does it know it? It has to depend on observing the environment. Somebody has to tell it how to interact with it. But the interaction is not always the same. So different users would like to have different kind of interactions, yeah? So what we have done is we let the system interact with the user to find out what the human wants. Simply, we have a set of objects and the robot and the human, yeah? And the robot will proactively suggest, hey, human, this is what I can do for you. Do you want me to do it? Or do you not want me to do it? So what it does, it proposes a set of solutions. So here you have a set of objects, it observes a set of objects, and it can give you a set of solutions, yeah? This is what I can do. So this is a list of solutions that it can tell you, this is what I can do for you, yeah? And the user can select, yeah, what the user would like to do. But then the robot or the system does not give you endless lists. It takes into consideration what the human has chosen, and then reduces this list so that it only makes sense. Because if you're holding a pen and a book, most probably you're going to write something. You're not going to throw it away, for example. Yeah? We assume that the human is not stupid. So thereby, this kind of proactive interaction between the robot and the human, you can define how interaction can be, how different humans can want to encode this kind of interaction. But all goes well when there is no problem, yeah? But what happens, some deviations occur. So what happens if the robot wants to do something and suddenly all hell breaks loose? If the object is not found, or if the grasping fails, what happens then? So here, the robot tries to pick up an object. It finds it, but the human is a bit naughty, so he tries to cheat the robot. So the robot now realizes, hey, I failed. I knew that the object was there. I was very confident. I went there and I tried to pick it up, but the human is naughty, so he made me fail. But then it suggests, it realizes this. It realizes that it has failed, and it suggests what kind of other aspects it can do, how it can recover from these failures. And the user who is cognitively more flexible can choose better what is best for that scenario. And once this is taught to the system, if a similar failure is occurring in the next instance, it can simply reload this experience and then work on this aspect. So it's a different day. If you want to notice, I'm wearing a different shirt. So that's how you know it's a different day. But the same kind of failure happens. And then now the robot does not ask for any help. Yeah. So a similar kind of a failure. It just loads from its memory what was the action that it has performed when it had failed in a previous occasion. And then it just loads this experience and then tries to come up with a solution. So now we can see that it just automatically goes forward and then tries again. But here, what it is also taking into consideration is the feedback from the user. After it has succeeded the second time, it will ask the user, did the user like it or not? Because it has taken this time a decision on its own from a previous experience, yeah? But was the decision correct or was it not? So this is also important to verify. I mean, the user can choose to ignore that kind of a feedback, but it still asks the user, okay, did you like it or did you not like it? So that's how you can program a collaborative behavior and also tackle with some kind of deviations that are occurring. So now to the final part of my presentation. I would like to give you some insight into some exciting ongoing projects. Sorry, I don't want to play the sound. So this is a project called Felice, which we're currently working on. If you can observe, it's a production environment with assembling of car doors. If you observe closely, the conveyor belt is moving. So the users are standing on top of a conveyor belt, and the conveyor belt is moving. And the users should, the workers should complete a task within the given time frame. So they have to assemble, they have to screw, they have to do all sort of processes until the given time frame. Yeah. So in such kind of a system, it is quite useful to collaborate with robots, because robots on one hand can hand over tools to you. Yeah, they can hand over components to you. So if the robot can quickly realize, okay, this user needs my help, I can go to this user, hand over a part to him or a component to her, then it improves productivity. But what is more important is when you do this kind of handover tasks, yeah, it is very critical that you have to take the ergonomics of the user into consideration. So you have to take, where should I present this object? In which direction? Should I approach from the left or the right, from behind? Maybe not behind, because maybe the user is, surprised. So you have to take, these kind of categories into consideration. And in the project, we came up with kind of a criteria which takes the muzzle strain, the arm joint angles, the dominant hand, and the worker sense of safety into consideration. And then it kind of creates a map around the user. Yeah. So there are these green dots and also red dots. Green dots are safe zones, and red dots are not so interesting for the user. Yeah. And then we take this into consideration and then figure out how to hand over the task. So that is the Felice collaborative robot. So that is directly, so now we have a robot with, this is a different kind of robot. It's not the usual collaborative robots that you have. It's an 8-degree freedom of robot with a mobile manipulator. And now it is installed at CRF, so that's in Melfi, Italy. And then it is now making progress in handing over tools to the user in the right form, in the right instance in time. And you have to also figure out what is the correct moment in time that I have to release the tool. You don't want to release the tool before the user arrives. You don't want to release it too late. So what we do is we also take into consideration the force values on the wrist of the robot. So if the user is pulling, then we realize this, and then we also take the context that the user is approaching the robot from vision sensors. That the user has approached the robot, and now the user is pulling the screwing gun, and then we release it. Finally, we have so since we are talking about sustainability, we are talking about sustainable robotics. Till now, we have talked about. I have given you an introduction where we said robots can help sustainability. But I would also like to give you an example how in real-world applications robotics are playing a role in achieving this. So I will show you a use case of electronic vehicle batteries. So this is a pretty much known problem that we have many electronic vehicles. And if the efficiency of the batteries in the electronic vehicles are below 85% or so, then they're not useful anymore for the cars. So then you have to dismantle these batteries and then use it for secondary purposes. But dismantling the batteries is not an easy problem. You have different, they come in different shapes, they come in different sizes. The construction of it is quite challenging. And I just learned that it takes about 4 to 6 hours to dismantle one battery. And it's very hazardous. It is very dangerous that it is made of all sorts of chemicals. And so there is also this shortage of trained personnel. And another problem is if you have different kind of EV vehicles, you don't have any information of the component itself, where it was manufactured, how it was transported, how it can be dismantled, and so on. So whenever we talked about battery recycling, yeah. So first, what happens is you get a EV battery, you have to disassemble it, and then what typically happens is you evaluate after disassembling the different components in the battery. And then if some components are going bad, then you replace them with working components, reassemble them, and then recertify them for secondary applications. Yeah. So for these aspects, we have in the project the physical assistive system. So as we have shown, yeah, a robotic system can assist the user in doing some kind of operations, and then the user can also be guided in the process. Because it's very dangerous, it's critical that you observe the environment and then you warn the users at the right point in time if they're doing something hazardous. And there is also this aspect of information barrier. So there is no defined way in which the data is stored. So now we are talking a lot about digital product passports, which maintain the data from production till dismantling, but there is no set standard of digital product passports. They are now making it mandatory from 2027 that we have to have a battery passport, but still there is this missing aspects of it. So what we have to really do is to do a life cycle analysis. Yeah, life cycle analysis. So before that, maybe I show you some general approach. Yeah, so you identify the damaged modules, you disassemble the plaque, you replace them. However, when you want to introduce the physical assistive systems and the cognitive assistant systems, it's not easy to figure out, again, to detect the situation. Yeah, you want to be minimally invasive so that you don't destroy the part. So if you want to disassemble a battery pack, on the battery pack there are set number of screws. You have to unscrew them. You remove the plate, and then you have some kind of a glue that is attached. You have to really drill into the part. Yeah, when you're doing this drilling operation, it might be that you are drilling too deep, that you're breaking the component. Breaking the component is okay, but if it explodes, then that's a completely disastrous outcome. So you have very challenging aspect. So here what we would like to do is to use this cognitive assistant system so that can project some information onto the field. And then here you can see an example that it's dangerous for the user to touch the battery because it's in a certain state. And then the robotic processes could be fastening or losing different type of screws, and also separation of welding joints. Coming to remanufacturing again, as a whole, right now we have some use cases where robotics are applied, but it is still not possible to productively do that. The problem is we don't design for remanufacturing. That's the main issue. We don't design the batteries for remanufacturing. That's the missing aspect. Because you don't design it for remanufacturing, when you want to disassemble it, there is no way to disassemble it properly. There is no standardization for digital product passports. And the safety could be a very critical aspect when you're considering battery dismantling. And there is always this low volume, high mixture problem. So you don't have a single kind of battery packs. You have multiple kind of battery packs. But we always have to think that the human is at the center of it. So you have to always design your process with human at the center and then apply robotics on top. It is not the other way around. So we have to always have this at the back of your head. Good. So that's all for my talk. But now for some advertisement. So we are we have a topic group on sustainability at EU Robotics. It's a joint initiative where I'm co-leading the topic group together with Francisca, who's here. So we are doing quite a few events. So we are organizing workshops and webinars. Also with Carl, we have done this together with EU Robotics and the Sustainable Robotics group. And then we are also collaborating with the other initiatives. So please join us so that we can collaborate together to find out how robotics can help us in sustainability, and that robotics don't hinder sustainability. So that's also one other aspect, that you don't want to fill landfills with robots. So you don't want to create robots as problems themselves, yeah? Good, so that's all for my talk. Before I conclude, this is our team. I would like to thank, so this is not my work that I have presented. It's a joint work with my colleagues from the Robotic and Automation Systems and Visual Computing. And yeah, thank you very much for your attention. And we are always open for collaboration. It could be bilateral projects, it could be research projects. You have seen our research. If you are interested in some aspects of it, please feel free to contact me. And before I close, I would like to really thank Carl for inviting me for the fellowship, and also for Anya for taking care of us, and also Shirley and Michelle, who made it very nice, the transition from coming from Austria to Brussels, and also, yeah, this has been very, very nice. So also thank you very much, and then if you have any questions, I'll be very happy to answer them. Thank you.
Thank you, Sharat, for this nice presentation. And as before, let's start by the question online. So we have a question. Hello, Sharat. That's a wonderful presentation. How much can these robotics interfaces and feedback be applicable to an industry like pharma? How much do you think this can help in achieving sustainable practices and reduce carbon footprint in pharma segment?
Yeah, in pharma, you mean agriculture?
Pharma.
Pharma is medical?
I guess yes.
Okay. So we have done quite a few. I have not. We as Profactor have not done projects on pharma per se, but we have done projects in the medical field, yeah, in surgery and so on, yeah. So there, it is very imperative to be very precise. So we are working on aspects of brain surgery, where you have to be precise and accurate, and it's very hazardous if you mess up. So here we use robotics for precise operation, and the user is given interfaces to observe how the robot is approaching the human head. We have different kinds of interfaces or vision systems to monitor this, and then the robot itself, assisting the doctors who are remotely operating the robot. Because it is not always possible that you have, there is also shortage of doctors, that you don't get doctors to do the operation, yeah? So we are looking into to a possibility where a doctor can teleoperate from somewhere else, and the operation happens on site in different hospitals. So that is the example I can give you. However, in pharma, there are definitely robotics involved. They're doing quite good work. There is also at EU Robotics a topic group on lab robotics. So you can definitely have a look at it, where they deal more details into how robotics are applied to pharma. I think there you will get more answers. But I myself have not worked in pharma, so this is as far as I can give you an answer.
Okay, thank you. So there are no other questions from all the online audience. So let's start with the in-present audience.
Hi, thanks, Sharad, for your nice talk and presentation. My question is, I've seen you looked at environmental dimensions and also at the safety reasons for workers. Did you do also some form of acceptance surveys or asking the workers how they feel about working with the robots so closely together?
Yeah. So we have not done in the last project, it's still going on. But for the earlier projects, I have shown you different examples of human-robot cooperation where the human was putting the hand on top of the motor block and the robot stops. So this was the real system which was installed at BMW. And there we did some kind of user studies. So it was done in 2 steps. In the first, we just did a dry evaluation without any technology, without any system. And they were very skeptical. That they were not very inclined to work with the robots. So they were skeptical in saying, okay, is it going to be productive or not? But then once we have the system in there and how easy it was to set up the whole process, they were very happy to use it. So what I have not shown you is other kind of interfaces. So there are these kind of interfaces which look like small balls, yeah. They are kind of red balls that you can play with, and then you can simply place them on the motor block, and then the system detects where to do the screwing. So it was like a kind of a game for them to play around with, and there is always the skepticism before you accept the technology. But once they see it, and then once they realize that it is going to be useful and it is not going to hinder their work, it is definitely going to you're going to see promise in there. Thank you for the question.
We have time for other short questions.
Yeah, a direct follow-up question because of what you said. Did you include them in the design? You said you put up the technology and you said it's useful, but how do you know it's useful for them? Did you include them in the development?
So this project that I mentioned was a joint project with AIT. So the Austrian Institute of Technology, and they were doing the user acceptance and the user guidance thing. So it was Astrid Weiss from Vienna. I think she's working at Vienna, I think. So she was the one who was leading this kind of user design. So, and we collaborated with her. But as I say, it's not only our work that in the project, but we collaborated with her, and then she helped us with her team to design this, and also to define the user studies and acceptances. But yeah, during this project, it was very interesting that in the starting we thought, okay, hey, they are not inclined to use the robotics anymore. So are we going to install them or not? But then once they saw the actual system, they were quite impressed. And that was a really nice outcome, I would say.
Okay, so I think that there is no more time for questions, but we can discuss later on. And let's thanks again Sharat for the presentation.
Thank you.
Thank you, Sharat. I have many more questions, but I will ask them in a break. So we'll have a 10-minute break. So we'll start again at, let's say, 4:20 for our last speaker, Devi, who is an artist collaborating with us this year. And I'm really curious to see what his talk will be about. Thank you. Welcome back, everyone. I would like to introduce you our last speaker for today. Davy Brunet is one of the 2 resident artists of the BrIAS program this year. He is specialized in folding and combines art, science and technology. Since 2015, he has been using a large range of materials such as fabric, but also biomaterials. And I heard in the break mushrooms and kombucha, so I'm really curious if that will also come up. Now he focuses on Ori robotics, which focuses on the intersection of ecology and technology. And on his website, he says that he believes that a simple fold can help us understand better our world and improve it with applied innovations. Here is Davy Brunet.
Thanks. Thank you for the introduction, and first of all, thank you to Home, who enabled me to participate in this very inspirational for me program of BrIAS, and I hope that I will get back this inspiration as a more artistic point of view than scientific. So my presentation will talk about, of course, folding, so I'll explain to you a bit what I mean by folding throughout my work, and then I'll speak a bit on how I implement sustainable robotics in my work. So first of all, a few words about myself, because I'm an artist specialized in folding, and it's not a very common medium, we will say. There's no university of folding. All the professionals in this domain are autodidact. They come from other perspective. And I always say that I have this chance of, I dislike school, so I had time and paper with me to practice very early. And after school, nobody advised me to do an art degree, so I did. I have a background in social science with a master in urban planning. And I think this social background, social science background, gets back into my work. And as an artist, I think I'm really focused on research and teaching from the point of view of an artist. And after this master, I've also progressed a lot with the use of many collaboration with different disciplines, including learning a lot of technological skill in the Fab Lab here in Brussels at the Open Fab. So this is just a few words about myself, and now a few words about folding, because usually when I speak about folding, you have probably this image of the origami crane in mind. And actually, yeah, origami, literally, it means a folding of paper in Japanese. As an artist, I feel that I'm in a larger scale in the world of folding, and that origami is just one small round of this, and that I feel that I take in account folding both as a technique, as a medium of expression, and as a field of research based on many, many different disciplines. Because, of course, you can fold paper, but you can fold fabric, which is a totally different domain. Textile pleating is not about paper. And here in small, you have probably seen this image. It's a really point-in view of a very famous painting. It's the Mona Lisa. Probably everybody looks at their eyes. I'm more focused on the sleeve and the beautiful Yoshimura pattern that you can see here. And probably I think you've been experimenting much more textile pleating actually than folding, and you can do the same with your sleeve. If you get back to it on top, you will make some Yoshimura pattern appear. Well, it's between chaos and pattern, but it will be Yoshimura pattern. Of course, you can do it again with paper or other materials perfectly for some robotic arms inspiration, for example. But folding is not only a technique that we practice, it's also something that is governing and structuring us from our skin to our brain to our cells, like proteins or DNA. It's all kind of folded matter. It's not anymore paper or textile. And we are not the only living beings that have this folding that organize us. We are in this beautiful period where everything is flourishing, and that we can see the mathematical language of all these living beings being transformed. We talked about also the corals. They are also folded. And it's not only about living beings, but a mountain. If we look at it at another perspective, it's just a matter that has been crushed and that has been just folded in a way and throughout the years with another temporality, another scale. again, sound, you can hear me because there are some waves that are crushed in a certain way. And some could argue also that the universe, the Big Bang, is also about folded matter. But I don't have time to go into these details. That's just a quick glance on how I perceive folding as a prism to see the world and to connect things. And I feel that in the past decades, robots are now invited to this gigantic ecosystem, and that they participate much more in the multiple interaction that we produce. I really think that they don't not only produce solutions for very local problems or improving things, but that they transform the way we see interaction between things. And in my work, I've been more specialized. I have paid a particular interest to biomimetic robots, so robots that are inspired by animals or by living beings, like, of course, the famous, these famous robot dogs, but we've seen many of them. And my research is called plantoid, and so it's combining robots, special type of folding techniques, and inspired by plants, because what I realized is that the vast majority of biomimetic robots are inspired by animals only. And it's quite strange for me to see that this fact could be correlated to the fact that if you see the biomass on Earth, animals represent less than 1%. Actually, even mushroom weight more than us on the planet. And plants represent more than 80%, yet I still feel that we take them still really as either object to decorate our house or resources for eating, for producing things, etc. And that's, at least some scientists are beginning to acknowledge the fact that actually they can communicate in many ways, that they have multiple ways of intelligence, different intelligence that we have. And we have a few examples in robotics inspired by plants, but I think it's still quite a few, and that sustainable robotics has much to learn from nature, and mainly from plants, but also maybe bacteria, fungi. And I think one of the limitations that I hear sometimes, and I've heard it not so long ago about plants, that someone saying me like, yeah, plants cannot move. Why should I be inspired by plants to make robots? And I've done the test. I've sat down like for a day looking at the pen, and yes, actually they can move. In different ways, of course, in different temporality than us, but yeah, maybe we can get inspired by these. I've done this research, not on my own, of course. I've been collaborating for the past few years with the Defrost laboratory of INRIA in Lille, who are specialized in soft robotic and really helped me to prototype and create new artwork combining folding with robotics. And together we created two main robotic, so combining folding and robotic. It's these two. On the top you see the actuation system we invented, and on the bottom you see the folding that were created. So one is a linear actuator that we created to make this origami ball, which is a model by Yuri Shumakov at first, but many developed it in different ways. And the other one is a structural crumbling pattern. And just a quick video of, this is the prototype, and as an artist, I end up a lot of time doing large-scale installation. So this is one of the results of just a zoom on large-scale installation I'm doing with these new robotics. And again, searching for this hybridity between organic and technologic. And we have made many examples also of trying out things, of course, during this process of art and science research. And actually, I've bring a few folding that I'm going to demonstrate very quickly, just I think so that you can see, but you've probably seen in many projects that folding has been of great inspiration, I think, for many fields in science, and especially robotic, I think. They offer large deployment capacity, compact storage advantage. Yeah, spacecraft. We have many examples in science that use them. I'm not going to go into the details of why they're useful. I bet you will see more than me on why they're useful. I'm just going to show you a few of them, and I really be glad if you can manipulate them afterwards. I will make them also available, I think, tomorrow, so you can also have a play with them. But just a few of them. So the first one I show you that has been used a lot actually in science. The MIT, I think, invented a grabber for it with more pneumatic actuation. It has been used for the Seoul University to create wheels of robots that can shrink to go into narrow spaces. And probably the ones working in medicine could see this as a stent. So in another materials and in another scale, it's used to go in a vessel and to repair something or to avoid surgery, actually. I have a bigger version of it that I wanted to show you, but because again, I think changing scale or changing materials offers a different point of view. And this one I invented as an isolation capsule because there is many noise sometimes in the city, so you can go inside it if it gets too noisy at this point. But you'll see that quickly it gets to another point, and again, it can get to multiple shapes, and this is what it's interesting. On how it can transform and yeah, take multiple shapes. And I think the main interesting fact about folding, both aesthetically but mechanically, is that here is just one paper. From beginning to the start is one of the only technique where usually you don't add or you don't remove material. You change the way the structure is organized, and it gives it new properties. And the second large-scale one I want to show you, so this is structural crumbling. So this is really a kind of new technique which is like 20 years old. It was invented by Paul Jackson and developed by Vincent Forderer with the CRIMP organization, which I'm part of. And it's really about, again, getting inspiration from nature, because you will see the patterns here that apparently it's chaotically structural, but once we open it, there will be a clear pattern on it. And I just need someone to come with me because we need to hold it together. So you can just take the 2 points really tightly, and I'm going to open it. So here you see large deployment capacity and the pattern, which is an hexagon inside it. So yeah, you can, thanks. So this is one of the robots I'm robotizing inside. And this is made from actually a baking paper with Chinese ink. So quickly with one or two last one, I think in robotics arm, there's a lot of example of also of folding practice. This one is the spiral in action by Jeff Bainon. You've probably seen a variation also with a crissling pattern that is a lot used also in robotics. Basically, again, you can have a very flat foldable structure and yet something that deploys and that have a stiffness to it, and with like multiple degrees of freedom that could be shrink in multiple ways. And the last one I want to show is one that, yeah, in spatial application, there's a lot of examples. The first one, and the most well-known probably, is the Miura pattern. This is actually a variation from it, but it's really something that you might have seen. The first one who invented this pattern is Kyoto Miura, was an astrophysicist, and he was the first one, I think, to really apply origami to a next level. And it was sent through the Japanese spatial agency in space in the 90s, I think, as a solar panel, so that could deploy very quickly. And this pattern also is actually well known in the fashion industry. I work also with textile pleatings, which is another thing. And if you get it in another material, it's also interesting to see how things can transform. Here you have a more flexible matter, but so I made this with basically it's steamer that keeps the fold. So it's heat and humidity that keeps the fold. And what is interesting is that you can just crush it around, unlike paper, and if you take it apart, and it goes back to its shape. So we have a memory shape materials with quite, I think, a low-tech practice. Yeah. So this is just a quick glance on the possibility of folding, and I think that a lot of people see origami or folding as a very ancient art that yeah, it comes from Japan, etc., and that is very old. And actually, we see that the most greatest development for origami and folding has been made in the past 100 years or so. And there's so many more that could come from it. And basically, both from nature to art, design, inspiration, there's also quite recently a lot of mathematical and engineer inspiration that have taken part in this folding world, and that could have application in robotic in many, many, many fields. So this is a quick glance of the possibility of folding, and now back to a more reality subject about sustainability and how maybe I see sustainability in my work or in robots, in sustainable robots. And I always say that I'm a child actually of sustainability. I've heard it for the past 30 years. I grew up with it, and I feel sometimes a bit like Woody in this image. Like I've heard it so many times, and yet I feel that it's quite very paradoxical in terms of concept, because while I definitely like theoretically this concept, the facts show that, at least for ecology, we're not maybe going in the right direction. I don't know what's the right direction, but at least I think that this concept, who was more than 30 years old, maybe needs to be redefined or rethinked in another way. And I like, for example, this view of the SDG placing and replacing maybe the biosphere, or at least the ecological issue on a more urgent matter, and that we thought of long-term sustainability. But I think that, at least in my work, I sense that ecology has been something that is of growing importance. And I think that we see, and we talked a bit last week about this ecological anxiety, and I think I grew up a bit with this, but I feel that, at least as an artist, I have a role to play to also take part in creating new possible discussion to not be scared about the ecology and to tackle it in another ways. And I would like call for an 18th SDG, I would say, about like something about art, culture, or maybe imaginaries. And we see a lot of time also with robotic, when we speak about robotics in the debates with civil society, we end up a lot of the time, I think, with very binary debates between utopia and dystopia, between like, is it a good or bad robot? Will it create jobs, or will it delete jobs? And I think we see that it's showing that, yeah, we need to think more about also incorporating how we imagine these robots, and not only in the application that they get, but also on what they create in terms of subjectivity. I started, I think, to address a bit this issue parallel to my research with a workshop I'm doing with kids. It's called a origami insect workshop, where I'm trying in 1 week to make them create a small robot combining simple things, and we end up with swarm. It's not intelligent swarm, but it's a swarm. And I think also it's important, at least for me in my work, that now I'm getting more and more electronics in my artworks that are of paper. I feel that I have a kind of paradox in my work, talking about ecology and still using a lot of electronic that I think pose maybe problems in terms of how they are harvested, how is the condition in mining fields, how is like rare metals a problem for the future. And I think that tomorrow, like the smartphone, I mean, if robots are everywhere in the future, the condition of how they are produced, how they are also in which materials, it could be also questioned. This is why I'm working a bit on biomaterials to maybe change also the way I'm creating robots. And in this workshop, because I'm very curious, and while they are having fun, I'm also showing them like what's inside the robots, how is it composed of, and I'm trying to make them solder and to like create the robots or repair the robots. What do we do with a broken robot? And I'm almost at the end of my presentation. I think the last point that I wanted to talk about is a bit how I think that the SDG are structured, and now I think we have a struggle with sustainability because we still are thinking a lot in compartment, both in the discipline and both from the point of view. Like I always wonder when we speak about sustainability, is it sustainability for whom, for what, for where? Is it for human only? Is it? And I feel that it's, a lot of thinking is very compartmented, it's silo, and I think we all this is from school and university, learning things from one point of view each time. And I have a small example from Brussels to illustrate this. It's the Palais de Justice that you have here, and we have many jokes about the Palais de Justice in Brussels, and one of them that I like to tell is that it's a huge building. It's the biggest justice palace in the world for such a small country as Belgium. And one of the jokes is that it's saying that the building is such huge and we are such focused on repairing one facade and one facade and one facade that when we get to the fourth one, the first one needs to be restored again. And it's a never-ending circle. And I think that I feel that I see sustainability a bit, or ecological issue a bit like the Palais de Justice. It's such immense, it's such big that we need complex thinking or complex solution to incorporate other ways of seeing it. And actually, to finish off with the Palace, I grew up in Brussels, and also I've never seen it without the scaffolding on it. But I did see the installation of new scaffolding to support the old scaffolding. So I think also that sometimes we need to think in terms of sustainability for robotics, how when finding solution, we don't create other problems that and again, never-ending cycle. So that's about it for my talk, and at least for me, I want to continue in this sense of really combining, I think, art, science, philosophy, ecology, techniques, and also thinking in terms of when we say about ecology. I really like the words of Baptiste Morisot, who is a French philosopher of ecology, that he's saying that the ecological crisis that we are facing, it's also a crisis of feelings. It's also a crisis of attention to things, and not only to humans. And I think that's maybe, at least in my work, I like to, in the future, pay more attention to humans, plants, robots, and all of these together. So that's about it, and I'm open to questions.
Okay, yeah. So thank you, Debbie, for this very interesting presentation. I don't think that we have a question from the online audience. No. So, well, questions?
Thank you very much for a fantastic talk and very, very inspiring. One of the, I mean, of course, there is, with folding, there's this, well, there are interesting things at the level of their mechanical properties, but also their natural beauty. Another world that I find to be absolutely beautiful is the world of fractals and fractal sets. And I was wondering if there is an intersection between fractals and folding.
I'm not sure I have an example. I could bring an example tomorrow. In the field of tessellation, it's a type of folding. We have a lot of fractal to it. And yeah, I think behind all this folding, there's a lot of mathematics to it. I mean,
so are you able to make like a sort of, are you able to make self-similar structures by folding in a certain way?
Yeah, it's possible.
So you can see patterns and then pass the same patterns inside the patterns, etc.
Yeah, it's totally possible. I'm personally bad at math, so not me, but it exists, yeah.
Okay. I didn't mean it from a mathematical viewpoint. I really meant it from an artistic viewpoint.
No, it's totally possible. And then, yeah. But again, you're limited to, as an artist working with materials, I'm limited to the materials I'm using in terms of fractal to go in deeper and deeper.
Other questions?
Thanks. That was a really interesting talk. I'm wondering, you've mentioned that this cross-interdisciplinary collaboration is very important. And I feel like it's often, especially with the environmental aspects and sustainability, it's often more in silos. So roboticists, they try to work on something, and then you have, of course, the experts from the environmental domain who have been working on that. And I was just wondering, because you've worked with a lot of people with different backgrounds, how should that be more supported? And how was it for you to interact with other scientists or researchers or artists who are doing a lot of different things, and how to communicate with them? I can imagine that's quite challenging.
Yeah, I think it's a large question. And to why, I don't know, I say time and money. I mean, here is also a good example. We are two artists participating in debate with scientists. I think maybe we need to incorporate also civil society and other perspective. But I think that it's also about giving time, giving again attention to it, and sometimes I would see like false interdisciplinary from the artist or the scientist part. Sometimes I see like artists saying, yeah, I'm interdisciplinary. And they're only working in the fields of art, or scientists working in the fields of science, and they are only working in different fields of science. And I think that sometimes getting people from really different background or really different mindset will enable to, and afterwards I think that also it's about people who are curious, who can take the time also, who are able to be permeable to change of thinking. No.
Okay, thank you for a great presentation. I don't know why I'm thinking about this concept, but within medicine, there was a really tremendous collaborative effort between medicine and visual artistry. And the document that I think about, which everybody who has done anything in a medical field has consumed, is Gray's Anatomy, right? And because it's, you know, because Gray was a visual artist, but now we don't need visual artists, because we can take pictures, or we can create technological representations of different anatomical parts. And I wonder, when you think about your artistic presentation, because it makes complete sense to me that we need to understand, for example, this artistic and technological application of folding in the creation of effective robotics. Well, is that an outcome that you could foresee happening, where the artistry of origami will no longer be needed, because we'll have exhausted our need for new artistic presentations in the technology?
I'm not sure I get the question, but again, as an artist, I think that there's a large application to art, not just for entertainment, I would think of. Like, it's also, I don't know, a matter of questioning things, of debate, of, and yeah, maybe you can remove the aesthetical beauty of art, but you won't remove all the other aspects of it. And again, with my collaboration, at least with scientists, I've seen it in different levels, that I've probably nourished the science part in just application. That I'm not going to do the application. I'm not a scientist, but I've just put inspiration, and they get back to me some other ways of thinking, or just technical things that I need. I think that both can grow on really different levels. And yeah, I don't know if it answers. That's great.
Thank you for a very nice talk. How difficult is it to make those objects? In the sense, is it something which can be, I would say, produced in large quantities? I'll tell you, some of the things you've shown, like the tube which you turn around, etc. I would love to have it. My kids would love to have it. My grandchildren would love to play with it. And I can imagine that there is a real market for it, even though it's artistic as object.
Yep, yeah, there's a limitation to it, theoretically, I would say. Yeah, as for my point of view, so I've been folding for almost 20 years, I think now, so I think enough skills to fold a lot of things, even if large scale is getting a bit hard. I always say that I have a craft that I don't need anything else than my hand and paper, which is quite magical from a point of view of other disciplines, but at the same time, I'm working more and more with machines that pre-score my paper, that help me to get to another step, and most of the time, I even created tools that could get me to another step, and most of the time, I'm most thinking that, again, it's not like black and white, it's hand or machines, it's like I work with machines and tools to improve myself, and to get like into more details or the things that I lack in my work. And as to if it's possible, it's like anything. If there's a market for it, yeah, we will build the machines. But most of the time, for complex folding, it would require like 4 or 5 degree arms going in multiple directions. And most of the time, there's no market for one single object that's. So it depends on the object. But yeah, there are some origamis that are already in the market and that are made from machines. At least textile pleating, for example, has been transformed completely by the industry. In the past 100 years, all the dress that you see in accordion pleating is done by machines, or like semi-mechanical machines. The rest, complex pattern, done by hand only.
Yeah, and you know, building upon what you said, so the folding you're talking about essentially creates what's called the surface développable. That is, you can map this. I mean, by design, you can map whatever you have back to a completely flat sheet.
Yeah,
right?
yeah.
And so I was wondering, for example, with 3D printing, whether there are some possibilities in creating like other foldable items that may not be from, I mean, that may not map to a flat sheet to begin with, but that would also have like interesting properties. I've seen stuff that people do with direct ink writing, like these polymer structures that really have super interesting characteristics and similar to what you're showing, meaning you press on them and then start taking like weird shapes.
Yeah, there's a lot of labs or artists that have been using. One of them is actually Matthew Gardiner, who has invented this research of robotic. This hat that you see on his head is actually 3D printed on a textile, which makes it easier for it to fold it. There's also in the mechanical properties of many things. There is a lot of example of. I'm mostly using in my work monomaterials, but by combining many materials and who have different stiffness or so, you can have a self-foldable. There's a lot of self-foldable origamis that have been invented. Yeah.
Okay. So. Thank you again, Debbie, for this nice presentation. And and yeah, Shirley for the.
I would like to thank everyone online and here in person to attend this seminar. I hope I will see most of you tomorrow morning at the VUB. We'll be at the -1 at the AI Experience Center for the forum on sustainable robotic technologies, if I say the title correctly. Thank you, everyone. See you soon.